Welcome to Jeremy's IT Lab. This is a complete course for the CCNP ENCOR Enterprise Core exam. This course will cover all topics you need to know to pass the ENCOR exam. In the past few videos, we reviewed some fundamentals of Layer 2 and Layer 3 forwarding, but also dug deeper as required for CCNP studies. In this video, we will look at a topic I only briefly mentioned in my CCNA course, which is MTU. Maximum Transmission Unit. MTU is a fundamental concept of Layer 2 and Layer 3 forwarding. So let's dig deeper to get a CCNP level understanding of MTU. Here's what we'll cover in this video. First, I'll introduce what MTU is. MTU actually refers to a couple different concepts. One is the Ethernet MTU, sometimes called the interface MTU, which is the maximum Ethernet payload size. The other is the IP MTU, the maximum size of an IP packet before it needs to be fragmented. Then there is the system MTU, which refers to the default MTU values used by the device. I will cover each of these in detail. Then I will give an example of MTU significance, its role in GRE tunnels. Finally, I'll introduce Path MTU Discovery, which allows a host to discover the smallest MTU size in the path to the destination when sending traffic. And be sure to watch until the end of this video's quiz. We'll look at a bonus question from Boson Software's ExSim for ENCOR, my recommended practice exams for the ENCOR exam. So let's get right into it. What is MTU? The maximum transmission unit is the largest unit a device can send or receive from an interface. That unit is usually an IP packet, including the IP header. However, it doesn't include the Layer 2 header and trailer. In the CCNA course, I mentioned MTU in relation to fragmentation of IP packets. If a packet is larger than the MTU, the router will fragment it into multiple parts. In this video, we'll get much deeper into the topic. Note that MTU generally refers to two separate but related concepts: Ethernet MTU and IP MTU. Let me demonstrate. Here's an Ethernet frame. Notice that under each header and trailer, I wrote the length in bytes. I'm not including the preamble and start frame delimiter in the length of the Ethernet header. If you do include them, the Ethernet header's length is 22 bytes. But as I mentioned in the CCNA course, we usually consider them separate from the Ethernet header. The Ethernet MTU refers to the maximum Ethernet payload size. Note that the term payload refers to everything except the header and trailer. So an Ethernet payload includes the Layer 3 header, Layer 4 header, and the data, but not the Ethernet header and trailer themselves. Then there is the IP MTU, which refers to the maximum IP packet size, including the IP header. If a packet is greater than that value, it must be fragmented. Looking at this diagram, the Ethernet and IP MTUs look like the same thing. But in the next few slides, I will try to explain their differences as simply as possible. Then there is the TCP MSS, maximum segment size. It is a similar concept to MTU, but we will cover it in another video. So to summarize, MTU determines the maximum size of a packet, and therefore the maximum size of a frame, that can be sent or received by an interface. The default MTU is 1500 bytes. I mentioned this in the CCNA course. However, larger values can be configured. And how does a larger MTU affect network communications? There are both costs and benefits of larger MTU values. A larger MTU value can increase network efficiency. How does it do that? It increases the data-to-header ratio. As an extreme example, if every single byte of data needed to be sent as a separate frame, every single byte would need its own TCP header, IP header, and Ethernet header and trailer, and that would be very inefficient. There would be many more bytes in all of the headers than in the data itself. If you increase the amount of data that can be included in each frame, the efficiency is increased. Fewer bytes for headers and such, more bytes for data. So a large MTU value seems like a great thing, but there are downsides. A larger MTU value can increase the network delay because each individual packet takes more time to send. As one huge packet is being sent, others have to wait in the queue, which can cause delays. Also, with a larger MTU value, packets are more susceptible to corruption. Just for example, let's say there's a 1% error rate. Note that 1% is an extremely high error rate, but this is just an example. So 1% of all bits get corrupted, perhaps due to some electromagnetic interference affecting the signal. If each individual packet is larger, that means there is a greater chance of a corrupt bit in each packet. And one corrupt bit means that the entire packet has to be retransmitted. If the MTU is smaller, meaning each packet is smaller, the chance of each individual packet being corrupted is reduced. And if a packet is corrupted, the cost of retransmission is also reduced, because the packet is smaller. It takes less time to retransmit a small packet than a large one. So, as you can see, there is a trade-off. A larger MTU means each individual packet can be larger, increasing efficiency, but that can also increase delay and increase the impact of network errors. A smaller MTU value means each packet is smaller, which is less efficient, but the delay between packets is shorter, and packets are less vulnerable to network errors. Generally, you won't change the default MTU of 1500, but there are cases where you should change it. I'll cover one example in this video. Now let me introduce a few new terms. Jumbo frames are larger than the default 1500 bytes, typically defined as up to 9000 or 9216 bytes, depending on the source. The maximum supported size depends on the device. My home switch, for example, allows me to configure jumbo frames up to 9000 bytes. Super jumbo frames are even larger than jumbo frames, but they are quite rare. I think most network devices can't support super jumbo frames. Also, there are baby giant frames, which are larger than 1500 bytes, but smaller than jumbo frames. Typically, baby giants are defined as up to 1600 bytes. Let me demonstrate how MTU works by doing an extended ping on R1 in this network. To do an extended ping, just use the ping command without specifying a destination. The router then asks you to input the details one at a time. I've highlighted some of them here. Note that the options where I didn't specify anything means I accepted the default, which is the value in square brackets. For example, for the top option protocol, the value in square brackets is IP. I just hit enter to accept that default option and send a ping using IPv4. Note that after that, I specified 192.168.12.2, R2, as the destination. Here, I specified yes for extended commands. This allows you to specify further details for the ping, such as setting the DF bit. Do you remember the DF bit? It's the don't fragment bit in the IP header. When it is set, the router won't fragment packets, even if they are greater than the IP MTU. That means the router will drop the packets instead. And down here, I specified yes to set the DF bit for these pings. And here I specified V for verbose, which will display details about the ping such as the size of each echo request in the output. And here, I specified a sweep of ping sizes. Sweep min size 1496, max size 1505, and interval 1. This will send a series of pings, starting from a size of 1496, increasing by 1 until a size of 1505. Here are the results of the ping. Note that it indicates that the DF bit is set. The first 5 requests, requests 0 to 4, receive replies, but the last 5, requests 5 to 9, time out. Why is that? It's because R1 was unable to send the pings greater than 1500 bytes out of its G00 interface because of the default 1500 byte MTU. Because the DF bit was set, the packets couldn't be fragmented, so they had to be dropped. Okay, so I've given a general overview of MTU. Now let's look at those two values I mentioned before, Ethernet MTU and IP MTU. First up, Ethernet MTU. The Ethernet MTU specifies the maximum payload size of frames sent and received by an interface. Note that this includes both Layer 2 and Layer 3 interfaces, since both send Ethernet frames. And although the name is Maximum Transmission Unit, not Maximum Reception Unit, MTU is checked at both ingress, meaning when receiving a frame, and at egress, when sending a frame. Sometimes the Ethernet MTU is called the Interface MTU, although I prefer the term Ethernet MTU. If a frame's payload, meaning the Layer 3 header plus Layer 4 header plus data, is larger than the interface's MTU, it will be dropped. Layer 2 doesn't offer any fragmentation capabilities, so dropping the frame is the only option. Here's the structure of an Ethernet frame. Note that there isn't any field in the Ethernet header that can provide fragmentation, unlike the IP header, which we will look at later. And since we're talking about the maximum transmission unit, let's also review the minimum. Look at the very bottom of this diagram. It says 64 to 1518 bytes. As I mentioned in the CCNA course, the minimum size of a frame is 64 bytes, including the Ethernet header and trailer. If a frame is smaller than this, the device will add extra bytes of padding to make it 64 bytes. The default Ethernet MTU is 1500 bytes. This is defined by the Ethernet standard. So the maximum size of a frame will generally be 1518 bytes, or 1522 bytes when using .1q, because the .1q tag is 4 bytes. Remember, the MTU doesn't include the Ethernet header and trailer, just the payload. To check the Ethernet MTU of an interface, you can use the command show interfaces. I've highlighted it here in the output. Now let's change the value. To change it, from interface configuration mode, use the command MTU. As I've shown here, in iOS V, which I'm using for this demo, the maximum configurable MTU is 9600 bytes. In this case, I configured an MTU of 1600. I then did the same on R2's G00 interface, configuring the MTU as 1600 bytes. Now let's experiment with some pings again. First, I tried to ping R2 from R1. I'm not doing an extended ping this time, but I specified the size with size 1550 at the end of the command. However, the pings failed. Why is that, even though both R1 and R2 have an MTU of 1600? More than enough to accommodate the 1550 byte pings. Although R1G00 and R2G00 both have an MTU of 1600, the 1550 byte pings fail because switch 1's interfaces still have the default MTU of 1500. So let's change that. On switch 1, I used interface range to configure both G00 and G01, and set their Ethernet MTUs to 1600 as well, to match the routers. Then I tried the same ping again from R1, ping 192.168.12.2, size 1550. After increasing the MTU of switch 1's interfaces to 1600, the 1550 byte ping succeeded. So this experiment teaches one important lesson. If you are going to increase the MTU to allow baby giant or jumbo frames, you have to increase the MTU of every interface in the path to the destination. If one of the interfaces has a smaller MTU, it can act as a choke point and prevent those larger frames from being sent across the network. On switch 1, I used show interfaces G00. Look at the part I've highlighted. 5 giants. Packets received on an interface that are larger than the interface's MTU are counted as giants. So these 5 giants listed here are the 5 ICMP echo requests R1 sent before I modified the MTU on switch 1. The echo requests were 1550 bytes, but switch 1 G00's MTU was 1500, so the frames were dropped and listed as giants. Okay, that's enough about Ethernet MTU for now. It specifies the maximum Ethernet payload size that can be sent or received on a router or switch interface. Now let's look at the IP MTU. The IP MTU specifies the maximum size of an IP packet before it needs fragmentation, and the default is the same as the Ethernet MTU, 1500 bytes. If the DF bit is not set, packets larger than the IP MTU are fragmented, although if it is set, they will be dropped. I demonstrated this when I did the ping sweep with the DF bit set before. The router tried to send pings with a size greater than the MTU of 1500 bytes, but because the DF bit was set, it couldn't fragment the packets, and so they were dropped. Note that IP MTU applies only to layer 3 ports. Layer 2 ports on a switch are not layer 3 aware, so they don't think about the IP MTU. Here's the IPv4 header. Do you remember which fields are involved in fragmentation? It's these 3 here, starting with identification. The identification field identifies the original packet the fragment is a part of. Fragments of one packet will all have the same value in this field. Then there is the flags field, which contains 3 bits. Bit 0 is currently reserved and is always set to 0. Bit 1 is the DF bit. If it's set to 1, the packet can't be fragmented. Bit 2 is the MF bit, which stands for more fragments. Every fragment of a packet except the last one will have this bit set to indicate that there are more fragments in the packet. For example, if a packet is fragmented into 4 fragments, the first 3 will have the MF bit set, and the last one won't. Finally, the fragment offset field identifies the position of the fragment within the original packet, which is important so they can be reassembled in the correct order. Note that the IP MTU cannot be greater than the Ethernet MTU. Why is that? If layer 3 tries to send a 1600 byte packet, but the Ethernet MTU is 1500 bytes, the packet would be dropped. It simply doesn't work if the IP MTU is greater than the Ethernet MTU. And if you increase the Ethernet MTU of an interface, the IP MTU is automatically increased to match it. So, when explaining the Ethernet MTU, I set R1 and R2's Ethernet MTUs to 1600. And as I'll show you next, their IP MTUs were also automatically increased to 1600. Now, you can manually configure the IP MTU to be lower than the Ethernet MTU, but usually they will be the same. We won't be focusing on IPv6 in this video, but let me briefly mention the IPv6 MTU. The IPv6 MTU is a separate value from the IP MTU, which applies only to IPv4 packets. So, even if you modify the IP MTU, the IPv6 MTU will remain the same, 1500 by default. However, the IPv6 MTU functions the same as the MTU for IPv4. It just applies to IPv6 packets instead. Now, note that the standard IPv6 header doesn't have any fields that provide fragmentation. However, IPv6 can use extension headers for additional features such as fragmentation. Here is the standard IPv6 header format. There is no identification field, flags, or fragment offset field like in the IPv4 header. However, here is an extension to the IPv6 header that can be used to provide fragmentation. If this extension is not used, IPv6 packets greater than the IPv6 MTU must be dropped. They can't be fragmented. I'll explain more details about IPv6 later in the course, so don't worry about this for now. Just be aware that the IPv6 MTU is a separate value from the IPv4 MTU. Now let's see how to configure the IP MTU. First, I used show IP interface G00 to check the IP MTU of R1 G00. Note that it is 1600. The default is 1500, same as the Ethernet MTU, but because I configured the Ethernet MTU of G00 to 1600, the IP MTU was automatically adjusted. Let's try setting the IP MTU back to 1500. The command is IPMTU from interface config mode. Notice the IP MTU range that it allows me to configure. The max is 1600. That's because, as I mentioned before, the IP MTU can't be greater than the Ethernet MTU. The Ethernet MTU is currently 1600, so the max IP MTU is also 1600. In this case, I set the IP MTU back to the default of 1500. I then checked again, and the IP MTU is now 1500 bytes, the default value. What about the Ethernet MTU? I checked it with show interface G00, and as you can see, it is still 1600 bytes. So the IP MTU can be less than the Ethernet MTU, but not greater. Note that with an Ethernet MTU of 1600 and an IP MTU of 1500, the largest IP packet R1 can send without fragmentation is 1500 bytes. The IP MTU takes precedence. Let's test that. I pinged from R1 to R2 with ping 192.168.12.2, size 1501 DF bit, and the pings all failed. That's because the pings are larger than the IP MTU, and the DF bit is set, meaning they can't be fragmented. I then pinged again without setting the DF bit, and this time it worked. The packets are larger than G00's IP MTU, but R1 was able to fragment the packets as needed. Now, as I mentioned before, you will usually want the IP and Ethernet MTU values to be the same. But just keep in mind the rule that the IP MTU can be less than the Ethernet MTU, but not greater. Also, I mentioned that IP MTU only applies to layer 3 interfaces, not layer 2. As you can see, layer 2 ports on a switch do not support the IP MTU command. It shows up as unrecognized. If I made the switch ports layer 3 ports with the no switch port command, it would work. But while they are layer 2 ports, it doesn't. And as a final note, the IPv6 MTU can be configured with the IPv6 MTU command, rather than the IP MTU command, which only applies to IPv4 packets. Next, we'll look at a concept called the System MTU. Basically, the System MTU allows you to configure the MTU on a system-wide level, so you can modify the default MTU values. Note that interface-specific configurations, if you configure them, will take precedence over these System MTU values. But let's see how to configure them. First, I used show System MTU to view the System MTU values. There are 4 listed: System MTU, System Jumbo MTU, System Alternate MTU, and Routing MTU. The System MTU is the Ethernet MTU for 10 and 100 megabit per second interfaces, so Ethernet and Fast Ethernet interfaces. The System Jumbo MTU value is the Ethernet MTU for 1 and 10 gigabit per second interfaces. Note that on systems that only have 1 gig and faster interfaces, which is the case for most new devices, the System Jumbo MTU option doesn't exist. Instead, the System MTU is used for all interfaces. The System Alternate MTU option is a third MTU value that can be assigned to particular interfaces. For example, if you want a third option between the System MTU and System Jumbo MTU. My switch doesn't actually support this configuration, although it appears in this show command. Finally, the Routing MTU is the MTU for routed ports. So let's configure these. First, I entered Global Configuration Mode and used the System MTU command. Note that on this switch, I can configure a range from 1500 to 1998. I configured it as 1600, so all 10 and 100 meg interfaces will use an Ethernet MTU of 1600. But note that I have to reload the switch for this to take effect. Then I used the System MTU Jumbo command, and notice the range is from 1500 to 9000 on this switch. I decided to configure it as 9000, so all 1 gig and 10 gig interfaces on my switch will have an Ethernet MTU of 9000 bytes after I reload the switch. I then tried to modify the Routing MTU, but I'm actually not able to modify it. This switch doesn't allow me to configure it less than 1500, and since the System MTU is currently 1500, I can't make it any higher. So I just decided to reload the switch. When it comes back online, you can see the values I configured. The system alternate MTU, which my switch doesn't support, was automatically modified to match the system MTU. The routing MTU is still 1500, but now that the system MTU is 1600, I will be able to configure it to a higher value. Okay, let's summarize the system MTU. The system MTU allows you to configure system default MTUs. If no particular MTU value is configured on an interface, the system MTU value applies. However, if an MTU value is configured on an interface, that MTU applies. It takes precedence over the system MTU value. Now, note that not all systems support system MTU configurations. Some only support per interface MTU configurations. Some only support system MTU, and some support both. The iOS VL2 switches in CML, for example, don't support system MTU configurations. And my home switch, which I'm showing here, only supports system MTU, not per interface MTU. Others support both. It just depends on factors like the switch model and iOS version. Now let's look at an example where MTU plays an important role when using tunnels such as GRE tunnels. As you can see in the diagram, R1 and R2 are both connected to an ISP, and we will build a GRE tunnel between them over the ISP infrastructure. Here is the pre-configuration on R1, configuring a loopback interface, its G00 interface, and a default route to the internet. And the same on R2, a loopback interface, the G00 interface, and a default route to the internet. Feel free to pause the video if you want to examine the configurations. And now, let's build the GRE tunnel. Here is the configuration on R1. I created the tunnel 0 interface, assigned it an IP address, 192.168.1.1/30, configured R1's G00 interface as the tunnel source, and R2's G00 IP, 203.0.113.6, as the destination. Finally, I configured a route to R2's loopback interface, 2.2.2.2, telling R1 to use R2's tunnel IP, 192.168.1.2, as the next hop. Then the same on R2. Create the tunnel interface, configure the IP, tunnel source, and tunnel destination, and then a route to R1's loopback with R1's tunnel interface IP as the next hop. So, now the tunnel is ready, and R1 and R2 will use the tunnel to reach each other's loopback interfaces. Again, feel free to pause the video if you want to examine these configurations. Now let's review GRE and see the role MTU plays. Here's a standard IP packet, a maximum of 1500 bytes with the standard IP MTU of 1500. However, when sending an IP packet over a GRE tunnel, the structure is different. When using GRE, a GRE header, which is 4 bytes, and an additional IP header, which is 20 bytes, are added to the original IP packet. This can cause some issues regarding MTU. If the original IP MTU of 1500 is used, the total size will be 1524 bytes, exceeding the 1500 byte MTU. So we have to fix that. The IP MTU of this internal IP packet should be adjusted to 1476, which is 1500 minus 24 for the new GRE and IP headers, to bring the total size to 1500 bytes again. Otherwise, the 1500 byte packets will all have to be fragmented, which will greatly reduce network performance. As I've noted here, the outer IP header can still provide fragmentation, so the 1524 byte packets won't be dropped, but they will all be fragmented, which slows things down a lot for both the sender and the receiver. You should avoid fragmentation whenever possible. Now let's examine the tunnel interface. I used Show IP Interface Tunnel 0, and as you can see here, in Cisco iOS, the IP MTU of GRE tunnel interfaces is automatically set to 1476. No need to manually configure it. Now let's see what happens when I configure it to 1500, like the standard IP MTU. I get a warning message and a syslog message. Let's read the syslog message. Tunnel 0, IPv4 MTU configured 1500 exceeds tunnel transport MTU 1476. What's the tunnel transport MTU? I used show interfaces tunnel 0, and it is stated here, tunnel transport MTU 1476 bytes. This isn't the Ethernet MTU, and I just configured the tunnel 0 interface's IP MTU as 1500. So what is this value? Even after changing the tunnel interface's IP MTU to 1500, the tunnel transport MTU remains 1476. This value is based on the actual IP MTU of the physical interface that will forward the frames, which is R1G00 in this case. R1G00's IP MTU is 1500 bytes, so the tunnel transport MTU is automatically calculated as 1476, which is 1500 minus 24. Now, as you can see here, you can configure the tunnel interface's IP MTU higher than the tunnel transport MTU, but any packets larger than the tunnel transport MTU will have to be fragmented. That's what those warning messages told us. In this case, R1's G00 interface will have to fragment the packets before forwarding them. Let's test that out. After setting the IP MTU of R1's tunnel 0 interface to 1500, I did ping 2.2.2.2 size 1500. Remember, that means the total size will be 1524 because of the additional GRE and IP headers. The pings work though. I then used the command show IP traffic interface G00 on R1 to view traffic statistics on the interface. As I've highlighted, although R1 sent only 5 pings, it sent 10 total packets. It says 5 fragmented into 10 fragments. So the 1524 byte messages were indeed fragmented before being sent out of the G00 interface. Let me summarize. When R1's tunnel 0 interface sends traffic, G00 is the physical interface that actually sends the packets. Tunnel 0 tries to send 1500 byte packets, referring to the internal IP packet without the additional GRE and IP headers. When the new GRE plus IP headers are added, this results in 1524 bytes. 1524 surpasses G00's IP MTU of 1500. So G00 will fragment the packets before sending them. So to summarize tunnel transport MTU, it is automatically calculated and represents the largest internal IP packet size that can be sent without fragmentation. So, although I demonstrated it in this video, you shouldn't increase the tunnel interface's IP MTU to a value higher than the tunnel transport MTU. The final topic I will cover is something called Path MTU Discovery. I won't get into any details, just a single slide so you know what it is. PMTUD allows a device to dynamically discover the lowest MTU value in the path to a destination, and it is enabled on most modern devices by default, for example Windows PCs. It is designed to avoid fragmentation of IP packets, because fragmenting packets requires additional processing on both the host doing the fragmenting and on the host reassembling the fragments. Hosts with PMTUD enabled set the DF bit on outgoing IP packets. They do this automatically. Any device along the path with an MTU smaller than the packet will drop it, because the DF bit is set. It can't be fragmented, only dropped. That device will then send an ICMP fragmentation needed message back to the packet's source host. The source host will then reduce the MTU and resend the packet. This process will be repeated until the packet is able to reach the destination without fragmentation, in which case the source host now knows the MTU of the path. For example, here's a random packet from my PC to google.com that I captured with Wireshark. Notice that the DF bit is set on it. That's because my PC uses Path MTU Discovery to find the lowest MTU value in a path and adjust packet sizes as necessary. Here's a summary of the commands we looked at in this video. If you don't remember any of these commands, I recommend going back in the video to review. In the next lab video, we will look further at MTU and practice using some of these commands. Here's what we covered in this video. I introduced MTU itself, then the concepts of Ethernet and IP MTU. The Ethernet MTU refers to the largest Ethernet payload that an interface can send or receive. The IP MTU refers to the largest size an IP packet can be before it must be fragmented. System MTU refers to the system default MTU values, and they can be modified on some devices, depending on the model and OS version. Note that in general, you can leave MTU values at their defaults. However, there are cases where manual configuration is needed, so it's important to understand the concept of MTU. We also looked at GRE tunnels and how MTU plays a role. And finally, we briefly looked at Path MTU Discovery, which allows a host to dynamically learn the smallest MTU value along a path to a destination, so it can avoid IP fragmentation. There's still a lot more to cover about MTU, but I hope this video gave you a much deeper understanding of MTU than before. Okay, let's go to the quiz. And after the quiz, we'll look at a bonus question from Boson Software's ExSim for ENCOR. Okay, here's quiz question 1. Which of the following is the best label for a frame that is 20,000 bytes in size? Pause the video now to think about the best answer. Okay, the answer is C, Super Jumbo Frame. The typical MTU is 1500 bytes, and baby giants are generally defined as being up to 1600 bytes, so A is incorrect. B, jumbo frames, are typically up to around 9000 bytes. I didn't mention the term runt, D, in this video, but they are frames smaller than the minimum size. C, super jumbo frames, are frames larger than jumbo frames, so C is the best answer in this case. Okay, let's go to question 2. What are 2 costs or benefits of using jumbo frames? Pause the video now to think about the best answers. Select 2. Okay, the answers are A, increased data to header ratio, and C, increased impact of network errors. Increased data to header ratio is a benefit. It means more bits are used for data and less for headers, which is more efficient when transferring data over a network. Increased impact of network errors is a cost of using jumbo frames. If there is a single error in a jumbo frame, retransmitting that large frame takes much more time than retransmitting a smaller frame. B and D are incorrect because both should say increased rather than decreased. Okay, let's go to question 3. If an Ethernet frame's payload exceeds the Ethernet MTU of the interface it must be sent out of, what will be done with the frame? Pause the video now to think about the answer. Okay, the answer is D. It will be dropped. Layer 2 does not provide any fragmenting functionality, so if a frame's payload exceeds the interface's Ethernet MTU, it must be dropped. Okay, let's go to question 4. In the network below, R1's G00 interface has an IP MTU of 1550 bytes. What is the tunnel transport MTU of its tunnel interface? Pause the video now to think about the answer. Okay, the answer is C, 1526. The tunnel transport MTU is automatically calculated based on the IP MTU of the physical interface used as the source of the tunnel. Because GRE adds a total of 24 bytes to a packet, the tunnel transport MTU is calculated as 24 bytes less than the IP MTU of the physical interface. With the default MTU of 1500, the tunnel transport MTU will be 1476, but in this case 1526, 24 less than G00's IP MTU of 1550, is the correct answer. Okay, let's go to question 5. Which of the following commands configures the default MTU of layer 3 routed ports? Pause the video now to think about the answer. Okay, the answer is D, System MTU routing. It configures the MTU of routed ports on a multi-layer switch. It is a system-wide command and will be applied to all routed ports. But if you specifically configure the MTU on the port itself, that config will take precedence over the system-wide value. Okay, that's all for the quiz. I hope this video was helpful. Before wrapping up, let's take a look at a bonus question in Boson Software's ExSim for ENCOR. Okay, here's today's Boson ExSim practice question. Note that I am using the web app in this case, not the Boson ExSim desktop app. The desktop app is a Windows app which you can run on a Windows PC, but this web app you can run on any system. Windows, Mac, Linux, even a smartphone. So you can do practice exams, for example, on a bus, on a train, in a cafe, wherever you want. It's very convenient. Okay, so let's look at the question. You administer the network in the following exhibit. Let me zoom in a bit more. Okay, here is the network. We have 3 routers, A, B, and C, and it looks like routers B and C are connected with a tunnel, a GRE tunnel. Okay, you issue the ping 192.168.1.2 size 1500 DF bit command from router B. Okay, so from this router, we are pinging, it looks like the other side of this tunnel, which would be router C's tunnel interface. The ping size is 1500, and we are setting the DF, don't fragment bit. And the ping fails, okay? Which of the following is most likely the cause of the failure? Select the best answer. Okay, how about A, the DF bit is not enabled? Okay, that is not true. We specified DF bit in the command, so that means it is enabled, and that means the packets won't be fragmented. How about B, the system default MTU is 1400? Okay, that is not true. It says all routers are configured to the system MTU defaults, and on a Cisco iOS device, that is 1500. How about C, the GRE tunnel MTU is 1476? Okay, I think this is the correct answer. As I demonstrated in this video, because GRE adds 24 bytes, 4 bytes for the GRE header and 20 bytes for the additional IP header, you have to subtract 24 to get the appropriate MTU. So that results in 1476 because the default is 1500, as I described in this video. Now, why would this be a cause of the failure? Well, it's because the GRE tunnel MTU of 1476 is less than the ping size of 1500. Now, if the DF bit is not set, the pings can be fragmented, and they will be able to go across the network no problem, although it will cause some performance issues if there are too many fragments in the network. However, in this case, the DF bit is set, so these 1500 byte pings can't be fragmented, which means they are too large for this tunnel interface, and they will be dropped because there's nothing else to do. They can't be fragmented. Okay, I'll click on Show Answer, and C is indeed the correct answer. And this is Boson's explanation. This is all stuff I explained in this video, but I recommend pausing the video to read this explanation just for some review. And finally, at the bottom, it gives some references, both to Boson's own material, the ENCOR OCG, official cert guidebook, and also a link to some free Cisco documentation you can read online. Okay, so that was a quick look at Boson Software's ExSim for ENCOR. Before finishing this video, let me thank my JCNP level channel members. To become a member, please click the Join button under the video. Thanks to Jonathan Makara, Boson Software, Velvet Jacob, George Streeter, Funny Dart, Nasir Chowdhury, Devin Suku, Gustavo BR, Gerard Baker, Marcel Lord, Pavel M, Mr. Erlison, Dragos Hirnea, Zakib Shah, Mayor Salman, Mason Anderson, Vitaus194, Gina Lindley, Nehemia, Justin Watke, Bold1C1U, Mark Jackson, Michael Carroll, Gerald Guillaume, Gabriel Braga, Renan Marias, Hector Hernandez, Ali Polat, Maratuba, R. Nelson, Roji Kuriakos, Owad Arpad Konives, 5 Feet, Daniel Brown, Emiliano Correa, Tricky Mickey 123456, Scott Thompson, Jose Alvarez, Kevin Hayes, Hussein Yavuz, Samuel Tavares, Mustafa Ersoy, Dear Diso, Nasser Zahar, Alexandru Badic, Brian Grant, Georgi Gemejev, Ahmed Ismail, Dibya Swain, Tan No, and Arlen Plagaria. Sorry if I pronounced your name incorrectly, but thank you so much for your support. Thanks to you and my other supporters, I am able to make these videos and release them for free on YouTube, so I really appreciate the support. Another great way to support the channel is to like the video, leave a comment, subscribe, and most importantly, share this video with others. So, if this video was helpful, I'd appreciate it if you did any of those. Thanks for watching.